All right, so we're good. So again, hi everybody, welcome to GOCC. We're going to start today by just reminding us all of our community statement very quickly. We are all learning. Everyone has something to contribute and no one has all the answers. So please feel free to ask questions whenever you want, contribute anything you like. Today we have our speaker, our very own Mark Denker from the University of Kansas, talking to us about cut complexes and total cut complexes of graphs. So take it away, Mark.
Thank you, Katie. So, howdy. I'm Mark. I've been organizing this thing for a while, but I finally have the chance to give a talk because the speaker we had planned was unavailable. And so I got to turn a 20-minute talk into an hour-long talk. But it's fine. We had plenty of material to do that with. And so I probably turned a 20-minute talk into a 2-hour talk, and we will cut as we go. So this is my lovely project for I have with lots of collaborators, several of which are currently in the room. So there is Marge Meyer, there is Maria Jelic Milutinovic, Rowan Rollins, Sheila Sundaram, and Lei Shui. And yeah, no, this has been a wonderful project that we all got together. Why we have such a large list of collaborators, I'll get to at the end, but let's get started. So quite a few sections here, but first off, you know, this is a graduate online combinatorics colloquium. You're here for combinatorics. No guarantee you know what a simplicial complex is. So a simplicial complex is, for me, an abstract simplicial complex is just any collection of faces closed under inclusion. So I take some subsets. Good examples of simplicial complexes, very combinatorial simplicial complexes, are all subsets of size 4 or less. So if A, B, C, D is in my simplicial complex, so will A, B, C. All sets of edges that don't contain a cycle. So every subset of a set of edges that don't contain a cycle will not magically start containing a cycle. Simplicial complexes naturally describe a lot of things combinatorists care about. Conveniently though, because you get all subsets closed under inclusion, it's pretty unnecessary to describe all of the subsets. You just need to describe the biggest ones, because once you describe the biggest ones, everything else is included. So we just call the biggest ones the facets of our simplicial complex, and they will give you a complete description of your simplicial complex. You don't need to write all of the sets out. So this is an example of an abstract simplicial complex. I have my facets listed in the angle brackets because they generate my simplicial complex. They do not contain all of the faces. But often it's good to have pictures to go with our abstract sets. And so for that, we use geometric representations. And for that idea, I'm just going to take the set 1, 2, 5, and I'm going to draw a simplex, which is to say, in this case, a triangle between my vertices 1, 2, and 5. And then I have 2, 3, 5. I'm going to draw that lovely simplex here. And I've got 3, 4, 5. I have that simplex. And finally, I just have the facet 1, 4. So I'm just going to draw an edge there. And that's my simplicial complex. Notice that, you know, my two-dimensional facet 1, 4 is just a line here. And so I have the face. Because 2, 3, 5 is in my complex, I have the face 2, 3. And if we look at my picture, that actually showed up. I've drawn that line in. It's just I don't bother writing it down and don't bother paying attention to it. And also, all of these braces and commas are a real pain, so we just skip all of that and really hope our complex doesn't have more than 10 vertices, because then one-line notation becomes a pain. But yeah, so this is the geometric realization of an abstract simplicial complex. We look at this and we go, oh, this is some space. I can do topology to it. And that's mostly what we're going to be doing in this talk, is we're going to be creating a simplicial complex, and then we're going to be doing topology to it. Wonderful. So what topology are we going to be doing? So actual topology is hard. How do we turn this into combinatorial topology? My favorite way of doing this is doing what's called a shelling order on our complex, which is just a special way of listing out our facets in a particularly nice manner. I've given you the full definition here. Please ignore it. What you want to know is that shellings are a way of constructing your complex piece by piece in a nice manner, such that every piece fits together well with other pieces. And so ignoring this definition, let's see an example of how we'd shell these simplicial complexes. And I decided to keep this as slide flips. So here I've got my lovely simplicial complex. I see I've got the phase 1, 2, 5. And in order to shell the complex, I just order the facets. So here I've gone 1, 2, 5. And then I've added the facet 1, 4, 5. And this is a good ordering because it shares as much ground with the previous facets as it can. It shares an entire edge. That's a good solid way of putting it together. Then I can add, say, 2, 3, 5, still sharing as much ground as possible. And finally, like here we're sharing 2 edges, but that's okay. Like the intersection between these two has codimension 1. That's what we're looking for. So this complex is a shellable complex. The shelling order is, facet 1, facet 2, facet 3, facet 4. But if I look at a non-example, I could do a terrible way of shelling the simplicial complex where I start with this facet and then immediately try to add the facet on the other end. If I look at this, the way these 2 facets are connected is just at the vertex. That's a very flimsy way of connecting those facets. It'd be a terrible way to put together a puzzle. You shouldn't put together your simplicial complexes that way either. And so just because a complex is shellable doesn't mean that every ordering of the facets is going to be a shelling. How are we doing so far? I'm going to pause for breath. Okay, so if this is a shellable complex, there are, of course, non-shellable complexes. Just take our complex and remove and force ourselves to go 1, 2, and we have a non-shellable complex. The bow tie complex looks flimsy. There's no way you can put together this in a nice way. However, it's not sufficient just to look flimsy. It turns out that shellability has topological implications. It's not a topological condition, but it has topological implications. So if you are shellable, then you're homotopy equivalent to the wedge of spheres in the correct dimension, which means that, well, I have this annulus, and so the annulus is homotopy equivalent to a circle, which is a wedge of spheres, but it is a wedge of spheres in dimension 1, not dimension 2. And so I know that this annulus can never be shellable. No matter how I try to make my facets, no matter how I try to order them, I'm never going to be able to get the shelling of an annulus. And we can see kind of the idea of what will happen by trying to shell it right now. And so let's say I add this facet, and let's just color it in. And now I want to add another facet. So if I have to add along an edge. So let's add another along an edge here. Then maybe I'll add the one up here. And so we see at every step, I only have 2 choices because I only have 2 exposed edges with the way I've triangulated this annulus. And so I go along. Maybe I keep going along here for a while. Maybe I switch over. But here is the idea, because now I've added all of these facets to my shelling order. But if I tried to add this final facet, what does my boundary look like? Well, I've got this edge, which is good, but it's also going to intersect my previous facets at that vertex. And so that is codimension 0, uncovered face, or codimension 2, dimension 0, uncovered face in my intersection, not a shelling order. And so that's just kind of an idea of how we can understand shellings, how they interact with topology. Let's get into what's new, because, shellability has been around for decades and decades. Whereas the new stuff, I don't think I actually put any proofs in this talk, so we can ignore that slide. Before we can get to the cut complex, we should define the cut set. So a cut set is just a set of vertices where if you remove them, our graph is disconnected. A question in the chat. So you need to intersect at codimension 1 with every triangle. The rule of the shelling is your entire, every intersection needs to be contained in a codimension 1 face of the intersection. So technically this vertex and this vertex are also codimension 2, but they're contained in a codimension 1 face. So it's a technical detail I probably don't want to get too much further in the weeds with. Okay. Yeah, there's a reason I don't like actually defining shelling order. It's because once you're familiar with it, it makes sense, but it's annoying to define. But yeah, so cut sets of vertices, you remove them, you're disconnected. So the set 2, 3, 4 here is a cut set of this graph. It's wonderful. This is not a minimal cut set. If you just remove 3 and 4, you would have a disconnected graph. And so yeah, reasonable definition, but they do motivate the name of our simplicial complex, which is the cut complex. And so this is a new simplicial complex that we are defining from a graph. And so if you have a graph, you can define the simplicial complex as the complex whose facets are size v minus k, so whose complement is size k, and their complements are disconnected sets of size k. So the other way of thinking about this is that the facets are cut sets of size v minus k, or facets are complements of disconnected sets of size k. I prefer the facets are complements of disconnected sets of size k, because then I don't have to reindex. But let's actually see how this is constructed. So I have my lovely graph here, and I want to identify all of the disconnected sets. So let's do that. Disconnected set, well, 1 is connected to 2, 1 is connected to 3, 1 is connected to 4, 1 is not connected to 5. And so that is a disconnected set, which means its complement, 2, 3, 4, is in my complex. Ooh, wow, I wrote that very poorly. And now let's see here. That's all the disconnected sets containing 1. 2, 3 is not connected. And so 1, 4, 5 would need to be in my complex. And then there should be one other disconnected set of size 2. And this is audience participation point. What is the other facet of my complex? Okay, I'm seeing 1, 2, 4. So if I have 1, 2, 4, I'm missing the edge 3, 5. And yes, 3, 5 is a disconnected set. So 1, 2, 4 would be a facet of my complex. And so if I look at my simplicial complex, then I can just go ahead and try to draw this in, and hopefully I do it in the right order, because there's a right way and a wrong way to do this. Let's try 1, 2, 4 in the middle. So if 1, 2, 4 is the middle, 1, 4, 5 shares the 1 and the 4, and I've got a 5 here, and 2, 3, 4, there's the 3. And so this is my lovely cut complex for k equals 2. Any questions on how we made this? Okay. So we have this lovely cut complex. And if we notice, shellable complex, I can just shell the facets 1, 2, 3. That's wonderful. And this is not surprising, because way back in 1990, Froeberg had a theorem that related to whether or not particular edge ideals of graphs had linear resolutions. So this is really the edge ideal of a graph is any kind of square-free monomial ideal with generators of degree 2. It's a very algebraic concept. Luckily, and so he said that this thing had square-free resolution if and only if a particular graph was chordal. In 1996, Egon and Reiner had a particular theorem about relating linear resolutions of ideals with simplicial complexes, and in doing so, they created what would become the idea that of the cut complex. And so they took these simplicial complexes and they took these ideals associated with simplicial complex, and they showed that if G is chordal, then the simplicial complex is something called Cohen-Macaulay, which says that the simplicial complex, which, and in addition, the complex is shellable and vertex decomposable. Generally, these conditions are not all equivalent. Vertex decomposable is stronger than shellable, is stronger than Cohen-Macaulay. And so for these particular complexes, they were all equivalent. It was lovely. They didn't name these complexes. They're just like, yeah, there's some simplicial complex. We're going to work with them. But the original goal of this project was to extend this theorem and basically to figure out what other ideals constructed from graphs can have these nice properties. And in doing so, we constructed generalizations of the simplicial complexes that Egon and Reiner originally considered in 1996. And so their complexes are now cut complexes for k equals 2. And our complexes are now generalized this by saying, okay, what if your disconnected sets don't just have size 2? What if we consider size 3, size 4, etc.? I also realized that I've just been assuming people know what chordal graphs are. This is definitely not the case. A graph is chordal if it doesn't contain any induced cycle size greater than 3. You can think of them as very triangle-y graphs. But yeah, this is a definition that's going to come up a couple different times in this talk. But yeah, so this was the goal, extend this lovely theorem. And so what we want to do is we created a new class of complex, and we want to know right now just, are they shellable? So we're concerned about whether or not these particular complexes are shellable. We look back here and we go, ooh, this is a chordal graph. If I try to look at a 4-cycle, I see that it's not an induced 4-cycle because I've got this chord in it. So very triangle-y graph. This is a chordal graph. I got a shellable cut complex. Froeberg's theorem not disproved in my first 10 talk slides. But let's see an example of a non-chordal graph. So this does contain a 5-cycle because it is the 5-cycle. And so we can start trying to construct our cut complex. We see we have a cut set of 2, 4, 5, separating 1, 3. I see the chat is enjoying itself. And so as we continue to construct this complex, we should see that we should have 5 different facets in our complex. And so I put the 5 facets, but you may notice I cheated because I used 7 vertices to build my complex. There were only 5 vertices to start out with. And so there's actually a vertex identification that needs to happen. These vertices are the same. And so we see what we have actually constructed is a Mobius band. So the cut complex of the 5-cycle is a Mobius band, and that's not shellable because, well, it's basically an annulus. This is a 2-dimensional object that's homotopic to a 1-dimensional circle. Cannot be shellable. So haven't disproved Froeberg's theorem in my first 15 slides. Maybe by slide 20 we'll get there. Okay, so we have these new cut complexes. We've defined them. It would be nice to see if these things have any properties. Like if I tell you that this simplicial complex is a cut complex, what can you tell me about the complex? And the first thing is by definition, by the way we construct them, they must be pure. All facets are the same size. And so that's lovely, but that's literally the only property you can guarantee. Every single pure simplicial complex is the cut complex of some graph for some value of k. So this is an unfortunate fact because it means these things are arbitrarily awful. Pure complexes have many, many different pathological states. And so let's see an example of how we can construct this fact, because it is a very constructive fact. So you start with the simplicial complex you'd like to reconstruct. And you take its ground set of the complex of your complex and you make a clique in your graph. So here I've got my ground set 1, 2, 3, 4, 5. I have this nice clique on the graph, and then for each facet, so I've got the facet 1, 2, 5 here. I'm going to create a new vertex on my graph. I'm going to just call it F1, and I'm going to attach it to all the vertices contained in the facet. So I'm going to do that with each of my facets. I also have 2, 3, 5. So F2, 2, 3 is attached to 2, 3, and 5. And F3 will be, let's say that's 3, 4, 5. And then I've got 1, 4, 5 is my final facet. So and then the idea is now the K value I choose is precisely the K value I have to choose. So I know that in order to disconnect this graph, basically this clique is too highly connected. So I want to make it so that I have to cut away precisely these 3 vertices in order to get what I want, in order to disconnect my graph. So my separating set is going to be 1, 2, 5, and that means my K value has to be the number of vertices that didn't show up in that separating set, which is 1, 2, 3, 4, 5. Oops, that should be probably delta 7. My disconnected set is of size 1, 2, 3, 4, 5. No, it's 6. Great, I can count. But yeah, I'm looking for cut sets of size 3 because the only way to cut is if you are the neighborhood of one of these vertices. And hey, the neighborhoods of those vertices are precisely the facets of my complex. This example also highlights something weird about cut complexes, is that notice in my graph, I had way more vertices than showed up in my simplicial complex. Like the vertex F1 does not show up in the simplicial complex, but that's because it isn't in any of the faces. And so my simplicial complex hypothetically has a larger ground set, but unlike topologists and geometers with their simplicial complex, where every single vertex needs to show up somewhere in the simplicial complex, you can have elements in your ground set that don't show up in any faces, and so it's not there, and so I still get the pure simplicial complex I started with. I think we call I think of these as ghost vertices. Any questions on this construction? Okay, so every cut complex, or every pure simplicial complex is a cut complex. There are many, many pathological pure simplicial complexes, which is somewhat bad news, but there are some good news. There are some good news. There is good news. So in order to demonstrate the good news, we're going to have to do a little bit of topology lesson. So there is something called the link of a face in a simplicial complex. I think of it as all the different faces you can view from that face. The star is everything containing that face, and the deletion is what happens when you remove that face. These concepts are, maybe a little difficult to just word out, so let's see an example. Here is a simplicial complex, and here is my face. And so this is the star of my red face. Let's call this red face sigma. This is the deletion of sigma. And this is the link of sigma. So we see here the star sigma is this facet contained my face sigma. You do have to make a slight concession to the fact that these still need to be simplicial complexes. So even though the face 4 does not contain sigma, 4 still shows up in the star because you would like the star to be a simplicial complex. But the deletion, when I delete sigma, I have to delete everything containing sigma with it. And then the link is all of the faces I can view from sigma that don't contain it. So sigma can see 3 through this facet, and sigma can see 1, but sigma has no way of telling that 2 is there. You need to go through other faces. So that is the general definition of link, star, and deletion. Actually, something nicer happens when you do it with a single vertex. So here's my vertex V. Here is my star V. Here is my deletion of V. And this is my link of V. So Shaw had an excellent question. What about 4 and 5? Sigma can see those. So 4 and 5 are contained in sigma. So it's kind of like you can't see inside yourself. Like I can't see my own liver is basically the analogy to fit here. It's like they're too close, so sigma cannot see them. And this is a somewhat annoying fact because it prevents this fact I'm about to show about links of vertices from being true about links of general faces. Because if I look at the link of my vertice and I compare it with my deletion and my star, I see that the link of my vertex is in fact the intersection of the deletion and the star. And so that's just generally a true fact, that if you want the link of a vertex, it's the intersection of the deletion of that vertex and the star of that vertex, but not true of general faces. Okay. Some fun topological facts. Why did I bring that up? Because it turns out that links behave very nicely with cut complexes. If you want to find the link of a face in the complex, delete those vertices from your graph. Compute the cut complex of your new graph. And so we basically have full understanding of links by understanding the induced subgraphs of our graph. And for a lot of topological considerations, if you have a full understanding of links, you have everything you want. And so it basically says in order to understand these cut complexes, a lot of what we're going to be doing is understanding the subgraphs of our graphs. An immediate consequence. Oh, I actually decided to visually understand why this is true. So this is one of the last examples I added. Here I have this lovely graph. We've already seen it. We've seen its associated cut complex. I have a vertex in my graph that I'm going to delete. And so recalling what we just said, then that says that the link of that vertex should be all the different vertices that the vertex can see. And so it should just be the simplicial complex that looks like the path from 2 to 4, from 4 to 3, and from 3 to 5. So if this lemma is true, deleting the vertex 1 should give us this path. And so if we actually delete the vertex, I now get this new path, and I want to find the simplicial complex. Well, okay, I want to find all complements of my disconnected set, so all complements of non-edges. Well, 2, 5 is a non-edge, and so I should have 1, 3. 3, 5 is a non-edge, so I should have 2, 4. 2, 4 is a non-edge, and so I should have 3, 5. And are there any other non-edges? I don't believe.
There's no 1. It's not 1, 3. It's
Oh,
2, 2, 5.
2, 5. Wow. Impressive. Yeah. No, it shouldn't be 2, 5. It should be 3, 4. Because these are the actual cut sets. So 3, 4 is a cut set, as is 2, 4. So you can either think of these as the cut sets of size 2 or the complements of the non-edges. And so when I put this all in a line, I see that 4 should be in the middle and 3 should be in the middle. So I have 3 and 4. and 5 and 2 is the geometric representation. And I look back, 5, 3, 4, 2. It's exactly what I predicted it would be. So yeah, links, induced subgraphs, deletions, all these things come together. And the good news is shellability behaves well with link. So a graph can be shellable if and only if all of its links are shellable. So the whole complex is the link of the empty face. And which means that our graph is shellable if and only if all induced subgraphs are shellable. Which means that we can understand shellability as actually a forbidden subgraph condition. You're only not shellable if you contain some forbidden subgraph. And this makes sense because remember Froeberg's theorem, this was about the k=2 cut complex. This thing was shellable if and only if your graph was chordal. But what does it mean to be chordal? It means you don't contain an induced subgraph of the 4 cycle, the 5 cycle, the 6 cycle. So you have this infinite family of forbidden induced subgraphs, and if you avoid all of them, you're shellable. This is also bad news because it tells us that you're probably not going to have a finite list of forbidden subgraphs. Even in the simplest case, we had an infinite list. It was a nicely describable infinite list, but it was an infinite list. So this is kind of one of the questions in the project is still open, is can we characterize the family of these forbidden induced subgraphs for any k? For large k, it's probably hopeless, but the k=3 case is more amenable. These are some examples of some forbidden subgraphs for the k=3 case. The fact that they are all 3 regular, or not 3 regular, that they all have minimum vertex degree of 3 is not coincidental. We have results that say that to be a forbidden induced subgraph of k=3, you need a lot of special properties happening with you, but still a work in progress. So we can understand obstructions to shellability as forbidden induced subgraphs, and we're working on trying to understand how we might categorize these, or what families can we know are going to be obstructions. Okay, so that's one thing we're working at. But the other thing we're working at is a more constructive idea. Like if I happen to know that this graph gives me a shellable cut complex, what other graphs do I know will give me a shellable cut complex? Can I do graph operations to my graph and still understand what's happening with my cut complex? And so that is our constructive theorems. And we have things for lots of things you like to do with graphs. Disjoint union, join, wedge product, all are understood in the idea of shelling. So disjoint union. If you have 2 graphs and they're both shellable, then the disjoint union of those graphs will also be shellable. It's very nice. It turns out that disjoint union behaves very well with shellability because cut sets don't actually care if your graph was connected to begin with. So as long as you don't accidentally delete all of the vertices from 1/2 of your disjoint union, then you're guaranteed to end up with a disconnected set. But yeah, disjoint union behaves very nicely with cut complexes. Join does the exact opposite. Join will break shellability, basically, if at all possible. So here, if you take the join of 2 graphs, then the complex will not be shellable if both of those actually had a non-void cut complex to begin with. So it's important knowing that if you take a clique as a graph, remember the cut complex is defined as the complement of all disconnected sets of size k. Well, you can't have a disconnected set of size k in the complete graph. And so the cut complex for the complete graph is just the void complex. That's all it is. And the void complex is the simplicial complex with no faces whatsoever. And so if both of your graphs are sufficiently sparse in order to have any disconnected sets of size k, then their join will lead to something that is no longer shellable. And yeah, again, this kind of behaves well with the chordal case, because it turns out when you start taking joins of graphs, you end up with a lot of 4 cycles if something hasn't gone right. Okay, but there is good news, because while join breaks things, if at all possible, if it isn't possible to break things, if one of your graphs was too connected to have a cut complex, then you do preserve shellability. All you've done is coned your complex like a bunch of times. And so this is a useful corollary that adding a dominating vertex is going to preserve shellability. And so disjoint union preserves shellability, join breaks shellability, dominating vertices preserve shellability because they're not complicated enough to actually cause a problem. And that actually gives us an entire class of graphs now that we know have shellable cut complexes. Because it turns out threshold graphs are graphs where you take a vertex and you add isolated vertices and dominating vertices in some order, show up in a lot of different places. And well, that is a disjoint union and join with a single vertex. Those operations both preserve shellability, so this thing will always be shellable. That was nice. This was one of the first things we realized in this project. But we also have another result for wedge products. And so if you were at the talk last week, you've already been introduced to the wedge product. If you're not, if you weren't, then that's okay. So the wedge product is the same as it is in topology. You take 2 graphs, you pick a vertex on each graph, and you just glue them together. They're now the same vertex. It's a weird operation on graphs because it's not unique. If I, instead of gluing those 2 vertices, instead glued vertex 5 to vertex 4, I would get a different wedge product. Like those graphs would not be isomorphic graphs, because this vertex would now have a degree of 5, and there's no vertex of degree 5 here. And typically, wedge product does not behave well with graph properties that care about vertices. Wedge products work really well for properties that care about edges of graphs, because notice you haven't glued any edges together. The edges kind of stay the same. Like the difference between disjoint union and wedge product for edges is often nothing. But for vertices, it typically behaves quite poorly. So we were surprised that, in fact, wedge products of graphs also preserve shellability. It's a little more of a trickier argument to run down, but yeah, if you take 2 graphs, and they both are shellable, and these things are both chordal, so for k equals 2, they're at least shellable. Actually, I believe these are both threshold graphs. Then their wedge product will also be shellable. That gives us another corollary, because it turns out trees are wedges. This is a fact that was also shown last week. Take a bunch of copies of K2, wedge them together, you have a tree. And so all trees are shellable for all K. So yeah, all threshold graphs are shellable for all K, all trees are shellable for all K. We do have examples of graphs that are chordal but are not shellable for particular values of K. So starting at K equals 4, there are graphs that are chordal but are not shellable, but do not have shellable cut complexes. So these are surprising results. Okay, I feel like I just spent a good 20 minutes talking without pause. Now's a good time to pause for questions. Okay, I think we've got about another 10 minutes. And so for that, I'm gonna discuss the other half of this project. So this project was about extending Froeberg's, extending Froeberg's theorem by creating generalizations of these complexes defined by Egon and Reiner in 1996, which happened to be two cut complexes. But it turns out there are other ways you could have generalized those complexes, and that is the idea of the total cut complexes. What if you tried generalizing the complexes in a different way? So to define them, more graph terminology, an independent set of the graph is a set of vertices that share no edges. Very useful. And a vertex cover in a graph is a set of vertices such that every edge, not every vertex, every edge is adjacent to one of those vertices. So here I have drawn an independent set. Here I've drawn a vertex cover, and I've chosen them very suggestively because it turns out that the complement of an independent set is a vertex cover and vice versa. If you think about it, you realize that if the vertex covers are adjacent to every single edge, their complements, if their complement had an edge between them, then your vertex cover didn't cover that. And so these two things are in conjunction with each other, or dual to each other, I suppose, is the way to think about it. So the total cut complex is defined very similar to the cut complex. We just say, take all of your independent sets of size k, take their complements, those are your facets. You can also think of them as vertex covers of size n minus k, but they are complements of size k independent sets. So let's use that definition on our favorite graph friend. So let's first find all independent sets of size 2. Let's see here. I see that 1, 5 is an independent set of size 2. And so if I take its complement, I will get 2, 3, 4. And then 2, 3 is an independent set of size 2. And I take its complement, I'll get 1, 4, 5. And okay, well, 3, 5 is also an independent set of size 2. So I'll get 1, 2, 4. And so if I put these all into a simplicial complex, again, I need to be smart enough to figure out which one goes in the middle. I believe it's 1, 2, 4. So if I put a 4 and a 1 and a 2, then 1, 4, oh, I can put a 5 there, and 2, 4, I can put a 3 there, and shade those in. And that looks familiar. And no, that's not a coincidence, because that looks like the cut complex for k equals 2 of this graph. But if you think about it, a disconnected set of size 2 and an independent set of size 2 are exactly the same thing in a graph. And so these two complexes are always going to be the same. And that is why they're both generalizations of the complexes made by Egon and Reiner, because those were the two cut complexes. They are also the two total cut complexes. The link lemma also is going to be true for your total cut complexes. And so shellability of total cut complexes can also be understood as a forbidden subgraph criteria. And one other thing that's also true of cut complexes, but becomes more relevant with total cut complexes, is that these things are nested in each other. If you are the complement of, if you are a face and your complement contains an independent set of size 3, it also contains an independent set of size 2. And so you can nest these complexes inside of each other. And that is useful because it turns out we are going to want to use quotient topologies for these things. Okay, so those are just some quick observations. Unfortunate things about total cut complexes.
Hey, Mark,
yes.
I think we have a question.
Hi. So just to clarify, so the difference between a cut complex and the total cut complex is that the complement for a total cut complex, you want it to be an independent set, whereas for a cut complex, you just want it to be disconnected.
Yes.
Is that correct? Right.
Precisely.
Thank you.
Yeah, so that's precisely the difference. It's just we've changed that adjective. It's either independent or disconnected. So bad news. All of those lovely constructive theorems about like disjoint union and wedge product don't work for total cut complexes. They behave typically very poorly. If you take the total cut complex of size 2 of k equals 2 for just the cycle, that would be asking you to find oh, I wrote this wrong. I did not want 2, I wanted 3. I should say of size 3. If you try to find independent sets of size 3 of just the cycle C5, you will give up. It has no independent sets of size 3. If you try to do it of an isolated vertex, you will give up. The isolated vertex does not have an independent set of size 3. And so this thing, so delta T3 of C5 is the void complex. And delta 3T of K1 is the void complex. And so the void complex is shellable. So the disjoint union of these, you would like it to be shellable, but it's not, because we see if we add an isolated vertex to C5, now my independent sets of size 3 are exactly sets that contain X and then contain independent sets of size 2. And so it's exactly the 2 cut complex of just C5. And we've already seen what that is, that's the Mobius band. That isn't shellable. And so shellability not preserved by disjoint union. And in general, shellability behaves very poorly with disjoint union. So that's the bad news, is you can no longer just look at shellability on connected components. You now have to actually do a lot more searching in your graph in order to find these kinds of minimal non-shellable graphs. But there is good news, because while they behave very poorly with, or reasonably poorly with disjoint union, not very poorly, they behave very well with what are called simplicial vertices. And so a simplicial vertex is a vertex whose neighborhood is a clique, or a complete graph if you prefer. And elimination ordering is an ordering of the vertices such that as you delete them, the next vertex is now a simplicial vertex. And chordal graphs are precisely graphs who have an elimination ordering of vertices. So let's look at our chordal graph, see if we can find an elimination order. So I look at the vertex 1 and I look at its neighborhood. And if I look at its neighborhood, I see that it is a path, not a complete graph. And so 1 is not a simplicial vertex, but 5 is. 5's neighborhood is a copy of K2. So 5 is an elimination order. I will now delete 5. And now if I look at vertex 2, 2 previously wasn't a simplicial vertex because 1, 4, 5 again is a path. But now that I've deleted 5, 2's neighborhood is just 1, 4. And so I can delete 2 next. And now I'm left with a complete graph. And so I can eliminate the rest in whatever order I want. So let's just say 1, 3, 4. And so that is my elimination ordering for my chordal graph. And why do we care about this? Because simplicial vertices behave well with total cut complexes. So if you have a simplicial vertex that is not an isolated vertex, because technically isolated vertices, their neighborhood is K0. So if you have a non-isolated simplicial vertex, then you have just, if you delete that vertex, your complex is homotopy equivalent to the suspension of that. You just are suspending your complex by adding simplicial vertices. If you have an isolated vertex, then it's more complicated. It turns out that you're taking a quotient topology on your complex where you're quotienting out by successive values of k. But regardless, these things behave nicely with regards to our complex. And these homotopy equivalents would not be good enough for shelling, but it turns out there's more nice stuff happening in the background, which actually gives us that if G is chordal, it has elimination of order of vertices, and that gives us that it is shellable for all values of k. And we can actually go further because of all of those lovely properties of what removing these simplicial vertices did to our complexes. We can tell you precisely, like we knew because they're shellable, they're a wedge of spheres of the appropriate dimension, but we can tell you exactly how many spheres there are. And so it turns out it just depends on the number of connected components of your complex. If you have enough connected components, you get some binomial coefficient of spheres. If you don't, then you'll be contractible. And if you don't even have an independent set of size K, then you're the void complex. But this is a lovely result, completely kind of categorizing the complexes for all chordal graphs for all values of K. And that's kind of the big punchline for our total cut complexes. Here I've just put up a lovely comparison slide between cut complexes and total cut complexes. I'm going to skip past that to go to the thank you slide. So this project, the reason why I have so many collaborators is because it started at the Graduate Research Workshop in Combinatorics, which is a wonderful research workshop where you come in with a research problem and then you find people who want to work on it with you, and then you just go from there. And so it was lovely to get started. We originally had even more collaborators from the workshop that left early on, but they were very useful at the beginning of this project. So thank you to Natalie, George, and Dane. And also my master's advisor is the one who gave me this problem way back, 6 or 7 years ago. And so, this is all his fault. And it's been with this group of people that we've managed to make so much progress in the meanwhile. But that's all I have for my talk. For questions, I'm going to leave this slide up just as a reminder of what we've talked about. And thank you.
All right. Thank you, Mark. Let's all thank Mark. Yay. And then open up the floor for any questions. Well, if no one wants to go first, I have a question. And I have no idea if this question even makes sense at all.
Sure.
But you mentioned that for these cut complexes, the topology can get arbitrarily awful, right?
Yes.
Is there any notion of if we restrict to certain parameters on the graph, how bad can it get? So if we, I don't know, or if we restrict to a fixed K, or don't have a finite subset of the forbidden subgraphs, has that been studied at all? Okay.
So restricting K definitely can do nice things because, for example, when K equals 2, we know that Cohen-Macaulay implies shellable, implies vertex decomposable. Those things are not equivalent generally for pure simplicial complexes. So that's just the obvious one, but for K, for even K equals 3, and the not known case, we found some properties that all the complexes for K equals 3 will share. So if you restrict K to a particular value or a low value, yes, you can get guaranteed certain properties. As for putting restrictions on your graph, I think we have studied that less, although the answer is with enough restrictions, certainly. For example, if you forbid all of the following induced subgraphs, list whatever the family of forbidden induced subgraphs for K equals 3 is, then the K equals 3 cut complex will be shellable. And so certainly putting restrictions on your graphs will lead to that. We haven't gone deep into what different restrictions on graph would imply for the cut complexes yet, though. In general.
It would seem like it would be really hard and really cool to be able to say, if you don't have this certain structure in your graph, we know what the homology looks like. But yeah, cool. Thank you. Other questions?
Know that the independence complex is something people have looked at, and it seems like the total cut complex has a very similar definition. So the independence complex is, I believe, that the faces are these independent sets of any size, so it's not pure, but this sort of feels very similar to it. Is there a connection between the total cut complex and the independent complex?
So yes, it's a couple of things make it a little difficult in order to describe it. So one is that because we choose a particular K value, it's kind of like we've taken some dual and truncated, but because we set like K equals to 3, we ignore all independent sets of size greater than 3, but also we ignore all independent sets that only exist in size 2 and don't exist and cannot be extended to an independent set of size 3. And so that makes relating it with the independence complex tricky. The other thing, though, is that we mentioned earlier about Froeberg's theorem. So that has to do, Froeberg's theorem is originally about the edge ideal of the graph. The Stanley-Reisner ideal, or the Stanley-Reisner complex for the edge ideal of a graph is precisely the independence complex. And so, in fact, the 2-cut complex is the Alexander dual, I believe, I should be careful here. I believe the 2-cut complex is the Alexander dual of the independence complex. And so is the 2 total cut complex. But once we, and so with that in mind, these, you can find greater values of K in the K equals 2 total cut complex. So if you take the independence complex, find its Alexander dual, and then go through the process of finding the subcomplexes inside of your K equals 2 total cut complex, you can get them out of there. So there are relations, but it's typically difficult to chase down.
Thanks.
So I've got a question. So you have, so when you do not allow cycles of size bigger than or equal to 4, you get that the cut complex has a certain topological property.
Mhm.
Do you know, I mean, do you know what sort of happens if you do not allow cycles of size bigger than or equal to 5, bigger than or equal to 6, and so on, or if you do not allow a graph sequence, which may not be the sequence of all cycles, but something else, perhaps.
Right, interesting. So we haven't considered like what happens if you just take cycles of, greater than or equal to 5. Like what happens if you permit 4 cycles but still exclude 5 cycles? Some of our techniques would probably, like the simplicial vertex thing, just kind of, as soon as you allow 4 cycles, it just immediately fails as any way of understanding these things. But with cut complexes, it might be able to extend that. As for excluding other families, most of the work we've done with that has been trying to find families of forbidden subgraphs. So it's finding other subgraphs that we know will be minimally non-shellable. And so a lot of work has been done, like what happens if you include the join of a clique with itself, or the prism over a clique. And so it's like, this will always give you a family of minimal non-shellable graphs. But yeah, it's been through the lens of shellability so far that we've been investigating these families, and we haven't gone further into other topological properties that might be.
So why I'm asking this is because I'm reminded of kind of problems which people look at in graph theory, in Ramsey theory, for example, when you do not have a certain kind of minor or a certain kind of small graph as an induced subgraph, or something of that sort.
Yeah, no. So the thing we had is like, we're like, man, there are like 8 million different graph theory questions we can ask about this. And while there is 6 of us, there are still only 6 of us. And so, yeah, no, the amount of open questions we have, put to the side of like, well, this would be lovely to investigate, but, we would like to actually get this out the door first is extremely extensive. So yes, lots and lots of questions still to be both asked and answered. But we've spent, our project is, we're starting to get tired.
Thank you.
All right, last call for questions. All right, if there are no other questions, let's thank Mark one more time. All right. Thank you for joining us this week. I know and awesome. Marge just shared their archive paper in the chat. So if you want to take a look at that, go ahead and do that. Thank you guys for joining us. Join us again next week when I believe we will have Grant Barkley from Harvard talking to us. But for now, thanks for coming.